Hello guys, and I'm once again back with a new video, and this video is based on another interesting concept, and the concept is chemical equations. Yes, it's all about chemical equations, something that we think to be simple, right? Oh, that's chemical equation, that's not a big deal. We treat chemical equations like something very simple, and we all are familiarized with writing chemical equations from our very childhood, right? But there is something, or you can say some points or facts about chemical equations, or some ways to look at chemical equations which we often overlook or skip. So today in this video I'm gonna focus on each of those important points, or you can say facts related to chemical equations which we people often overlook. So as you people might have figured out from the title or the heading itself, chemical equations, what does this speak of? An anthropogenic or man-made approach to talk to chemical reactions. Yes friends, chemical equations that we write are man-made. The way we write chemical equations is man-made, right? And that is the reason why I have used the word anthropogenic, which means man-made. And writing chemical equations is a man-made or an anthropogenic approach to talk to chemical reactions, or to know much about a chemical reaction that I am interested with. Did you understand? So let me start with today's video without any more delay. So let's start from the very beginning of the page that I have prepared to explain you people through. First thing is that, as I have written here, let's start from here. So, a general representation of a chemical reaction. Yes, another definition of chemical equation is that it is a general, not a general, it's a representation of a chemical reaction. I have used the word general because in this representation I haven't mentioned any atom or molecule or ion, and that is the reason I have written A, B, C, D are molecules, atoms or ions, because I haven't specified, and that is the reason why I have used the word general in this case. Otherwise, chemical equation is a representation, right? It is a visual representation of a chemical reaction, and the symbols that we make use of, like capital letter C for carbon atom, capital letter H for hydrogen atom, even these symbols are man-made, because capital letter C, capital letter H, right, these are letters that we make use of to suffice our own requirements. So do not confuse with that, and that's a matter of common sense. You people, we already know that carbon atom doesn't look like capital letter C, or hydrogen atom doesn't at all look like capital letter H. Okay, so a chemical equation is a representative of a particular type of reaction, and it talks about the reaction. Okay, A plus B, as per the above representation is considered or concerned, A plus B is an expression that we have placed or kept on the LHS or left hand side of the given equation, and C plus D is another expression that we have put on the right hand side of the equation. Now this A plus B and C plus D, along with the equilibrium sign inserted in between them, constitute or make up an equation. Yes, this is what we actually mean by an equation, which we have named chemical equation. Now, we have deliberately or intentionally used a different prefix to create contrast and to make people understand what? Understand that it's an equation in chemistry and not an equation of any other subject. So it just to create contrast. So we have deliberately made use of the word chemical before writing equation, just to create contrast and to make people understand that we are talking something about chemistry or something related to chemistry. By naming it in this way, we have named it as we have named it, we have specified the type of equation that we are talking about. Yes, because we are talking about an equation that we make use of in chemistry and not in physics, or not in biology, or not in mathematics. But of course it has huge contribution of mathematics, because whenever we talk about equations, it's all mathematical, right? And even this is a mathematical way to represent a reaction. That's another definition of a chemical equation. That chemical equation is a mathematical way or a mathematical form, or you can say a mathematical look of an equation that we are talking about. Okay, a chemical equation is somewhat similar to field. We people have already discussed field in the previous videos. If you haven't watched my videos on field, do watch them, because I have tried my best to explain the real meaning of field to you people in a different way, or you can say using visual imagery. Okay, so in their roles, so I have said that the chemical equation is somewhat similar to field in their roles, or actually they are similar in their functions, or what they do, or what they have asked to do. Why? Because a chemical equation provides us with necessary or you can say many necessary informations regarding the reaction that we wish to focus on. For example, I want to study the above reaction, that is A plus B gives us C plus D. Now to before studying this reaction, we need someone who will tell us lot many things about it, so that we become familiarized with the reaction that we are going to deal with. So this is what we are gonna deal with. And chemical equations serve as a guide or a person who will provide us with all sorts of informations about a chemical reaction that we are going to deal with. So it's like a guide, or you can say it's like a man who is gonna tell you many things about a chemical equation to make you familiar with the same. So now here, as I have said, regarding the reaction that we wish to focus on. So in this way, chemical equation acts like a messenger, just like field, right, to transfer messages. But here chemical equation is different from field, because chemical equation is not created by chemical reactions, right? Chemical equations are not something that is created by chemical reactions. Chemical equations are anthropogenic or man-made. It's made by us to make the things look simpler. That's all about chemical equation. So let understand this thing visually. As you can see, here is a door, and above the door there is a signboard where something is written. Reaction is going on inside. Okay, so some sort of reaction is going on indoor. So this guy is saying something. Let's read its dialogue. Hello sir, I'm chemical equation. I'm here to tell you many things about the reaction which you have decided to study. Please correct it. It will not be who, it is going to be which you have decided to study. So the reply comes from him. That's nice. Yes, it's good to know about the reaction before I deal with the same. And this guy says something more. I'm here to provide you with many informations about the reaction, and I will ensure that you will left with no doubt. Right, or you are not left with any doubt. So this individual represents a chemical equation, or we can take as if this individual were a chemical equation, and this individual is the observer. For example, the one who gonna study the reaction, and the reaction is going on indoors. So before entering into this room inside which the reaction is going on, this is the guide for this person to tell many things about the equations to this person, so that this person get familiarized with the chemical reaction that he is gonna deal with when he will enter into this room through this door. This was a kind of brief introduction about chemical equation. I have also made many other attempts to explain to you what chemical equation actually means. So let's turn over the page and go to the next page. So here is the next page. So I have written something. So let's begin with what I have written. We study reaction of a particular type. That doesn't mean only one such reaction takes place in the system. Many such reactions occur in the system, but when we study the reaction, we study only one such reaction because we are concerned with the type. Exactly. If I say that in an examination hall, 100 students are writing the same exam, and I want to know the questions, or I want to just explore the question paper, then what shall I do? Then it's a matter of common sense. Once again, I will ask for a question paper and I will go through it, and of course I will not visit each of those students or their benches to see or to read their question paper one by one, right? Because that's gonna be a foolish task, and of course no one will make that mistake. Fine. So there, for example, if I say, let's talk about a visual example here. There is a basket filled with 20 apples. How many apples? 20 apples. If I want to know about apples, I will study one apple instead of studying all 20 apples. Exactly. You know what matters most? What matters most is type. Even in genetics, in biology, genetics chapter, we are more concerned with the type. When we are provided with the type, or when we come to know about the types, we are least concerned with the number, right? Especially when we are dealing with the gametes and the types of gametes, right? Even in the Punnett square or the checkerboard, we focus on the types and not on the numbers. Many students misinterpret it and think that in the Punnett square, what we write in the small boxes are the numbers. There are 4 boxes, that means this 2 individuals can produce only 4 individuals. No, the concept is wrong. And the same applies here. We are concerned with the type. One chemical equation talks about one chemical reaction, right? One chemical equation talks about one chemical reaction. One chemical equation, that means each chemical reaction has a corresponding chemical equation that we can write or frame. So who tells the story? The chemical equation. And what is the story all about? It's about the chemical reaction. Did you people understand? So we basically focus on the type. If there are 3 things and of the same type, by dealing with one such thing, we will come to know what's going on with the other 2, right? Okay. There is a basket filled with 20 apples. So if I want to know about apples, I will study one apple instead of studying all 20 apples. Now if I say that there is a book on apples which provides us with many infos about apples, then this book can serve as the representative of a chemical equation. Let's assume that this book is a chemical equation, right? And let's say that this apple is a chemical reaction, and this basket full of apple is the system. As I have said, in a system, numerous reactions are going on, right? And the reactions are of the same type. Did you understand? For example, if I have taken 10 lakh molecules of A and 10 lakh molecules of B, we will get a finite number of C and D as well. But the reaction is same. That means many reactions are taking place, but the type is same. That is A plus B giving us C plus D. So when the type remains the same, by dealing with only one reaction, that is A plus B giving us C plus D, we can easily understand what's going on with the other. Did you understand? So I have done the same. If this is the system containing many reactions, these apples are the reactions here. I am plucking out one apple, or I'm bringing one apple out. That means I'm isolating or taking out one reaction from this system to study it. So this represents a chemical reaction of a particular type. We have taken the apple as if it were a chemical reaction. Of course, apple is not a chemical reaction. Try to understand, guys. It's just a representation or an analogy. And this is the book that I was talking about, book on apples. So this represents a chemical equation. We have to read the book to know about an apple, and then we can deal with an apple. Likewise, we have to go through a chemical equation before we deal with its corresponding chemical reaction, because a chemical equation is like a guide or a reference book of a given reaction. To know a chemical reaction in a better way, what we need is a chemical equation. That's what we have to take the help from. Why did I say that the approach is anthropogenic? Yes, I have already answered this question. It's because the way we write an equation and the designations and or the symbols that we use to indicate various elements are man-made. A hydrogen atom doesn't at all resemble capital letter H, or a carbon atom doesn't look like capital letter C. Yes, we know this very well. Let's go to the next page and talk briefly about equilibrium. I've decided to make a separate video on equilibrium, so I have not written much about it, which I will talk about in another video, but I will give you a brief idea about these three signs which used to confuse me a lot. Believe me, in my school life, no teacher could clarify this doubt properly, but I stuck to it. And what happened is that after going through it many times, or a number of times, I came to know the real reason behind writing these three signs or behind using these three signs. And today I will clarify the doubt. If you people have the doubt, then it's gonna be advantageous for you people, because I'm gonna clear it out both visually as well as numerically. Okay, so let's talk about this sign. What does this sign represent? This sign is indicative of the fact that the system can reach, it's not reached, okay, it's reach. System can reach or is already at equilibrium. What does equilibrium mean? Equilibrium is a peaceful state where every system wants to reside. It's free from unnecessary chaos and turbulences. You can see this visualization that I have drawn. So he is meditating. It's a meditating system. And this system is very happy. You can figure it out from the smiley face I have drawn. And there is a signboard where it's written at equilibrium, don't disturb or do not disturb. So system, actually every system wants to achieve equilibrium, because that is a kind of serene, tranquil, peaceful state. But there is no disturbances, no worries, nothing. And that is the reason why when you try to disturb it, according to Le-Chatelier's principle, the system tries to reacquire or go back to the equilibrium state, because no one wants to lose it. In a sloping ground, if I say that there is a sloping ground, for example, there is a sloping ground and there is a ball kept at its bottom, right? If you take this ball here like this and leave it, the ball will come down. That means the ball doesn't have any tendency to stay here. Why? Because this is the equilibrium position of the ball and not this one. So as soon as you leave the ball, as soon as the ball is freed, or as soon as we let the ball free, it will automatically come here of its own accord, because it loves to stay in this position. This is the concept of equilibrium. I hope you people have understood. So, and what is the meaning of this sign? Meaning, both the sides of the equation are almost equally favored. That means, see the two arrows. There is no difference between the length of these arrows, but there are differences in the length of these two arrows. I will talk about them later on. Here itself, but I will talk about them later on. So what does these represent? Here, both the sides of the equation are almost equally favored. That means, right hand side and left hand side of the equation are equally favored. That means there is no partiality which is observed. Let's say at equilibrium A plus B gives us C plus D, means concentration of that. So here we have used this symbol and neither of these symbols, right? Okay. So A plus B giving us C plus D, fine. Means concentration of products and that of the reactants are comparable. Let's understand this using an example. For example, 20 A's and 20 B's were there initially, and at equilibrium, what we found is 15 C's and 15 D's. Did you people understand? 15 C's and 15 D's. That means at equilibrium there were 15 C's and 15 D's. But the numbers are close, 20 and 15. So 20 and 20B should have produced 20C and 20D. But we are getting 15D and 15C. That means That means 5 A's haven't reacted with 5 B's to give 5 C's and 5 D's. Okay, fine. This is the case because nothing is 100% efficient, right? We cannot say that 20 A's will react with all 20 B's. It may not happen because nothing is 100% efficient, right? 100% efficiency is a theoretical concept, so try to understand. But since these two numbers are close, 20 and 15, there is a very less difference between these two numbers, right? They differ by 5. So the thing is that we use this symbol in this case because the two sides are comparable at equilibrium. Don't forget, I'm talking about what I have observed at equilibrium, or when this system is at equilibrium. That means peaceful state. Okay. Now if I come to example number 2, let's see. 10,000 A's and 10,000 B's. Right, there were 10,000 A's and 10,000 B's initially, but at equilibrium I got only 6 C's and 6 D's. What does that mean? That means 9994 A's haven't reacted with 9994 B's to give 9994 C's and 9994 D's. But this time 6 is very small in front of or in relation to 10,000, and thus it becomes ignorable. Means we can ignore this quantities or this number 6 if we want, because it has become negligible. If you don't believe, go and ask 10,000. 10,000 will say that I am so massive and so big that it is very difficult for me to detect 6. Try to think about Godzilla. Godzilla is just walking over the road, and suddenly you come or reach near its foot. Will it be able to detect you? Even if it has good intentions, it might happen that the Godzilla will squeeze you down its feet because it might be an accident, right? Try to think. It's another representation. So we can say you are negligible or ignorable with respect to Godzilla, isn't it so? The case is something like this. So in this particular case, we are going to use this sign. Just think about this. If at equilibrium the scenario is like this, that means the reaction doesn't want to take place. That means many A and B's are left unreacted. Many A's and B's just stayed unreacted. They didn't react at all. So it seems as if the reaction is not a favorable one, or the system don't want the reaction to proceed forward, or the reaction has no tendency to proceed. That is why this one.